Well, good evening, everybody. Great to see you on this cold, wet, pre-winter evening. Thanks so very much for braving the elements and coming out to be with us tonight. I am David Cole. I'm the president and CEO of the Science History Institute, and we are delighted to welcome you to the 35th annual Ullyot Public Affairs Lecture featuring Nobel laureate Sir David MacMillan. This annual lecture was endowed by chemist Glenn Ullyot, who believed passionately that chemistry, biology, and physics are the keys to understanding our world. His vision was simple but powerful. Give those advancing science a forum to share their work, allowing the public to see directly how science transforms and informs our everyday lives. I believe he'd be pleased with this legacy as it continues to connect the public with people of extraordinary scientific accomplishment who have advanced human knowledge and improved our world. Among past Ullyot lecturers are Robert Langer, Philip Sharp, Jennifer Doudna, Roald Hoffman, Francis Arnold, Carolyn Bertozzi, and most recently Omar Yaghi. The list is now joined by Sir David W.C. MacMillan. This annual lecture is particularly important to the Science History Institute because it lets scientists at the forefront share their journeys directly with you. There is no better way to understand breakthrough science than hearing about the successes, the setbacks, and those aha moments from the researchers themselves. It is our mission to bring these stories of groundbreaking innovation and life-changing science to everyone. We are grateful in this mission to collaborate with outstanding partners on this lecture this evening, including the Department of Chemistry at the University of Pennsylvania, the Department of History and Sociology of Science at the University of Pennsylvania, the Department of Chemistry and Biochemistry at St. Joseph's University, and the Philadelphia section and the Delaware section of the American Chemical Society. Thank you to all of those organizations for being our partners in this. Together, we're pleased to bring you the 35th Ullyot Public Affairs Lecture, celebrating a lifetime of achievement and contributions to humanity. This evening, as I said, we're very happy to welcome Nobel laureate Sir David W.C. MacMillan to Philadelphia. Following his talk, which is entitled The Path to Invention and Discovery in Catalysis, there will be a question and answer period, followed by our award presentation. During the Q&A, and I see there are a lot of you out there tonight, during the Q&A, if you have a question, please raise your hand, and one of my colleagues will do their best to find you with a microphone. And now a bit more about our distinguished speaker. Sir David MacMillan is the James S. McDonnell Distinguished University Professor of Chemistry at Princeton University and a Ludwig Distinguished Scholar. Born in Bellshill, Scotland, he received his undergraduate degree in chemistry at the University of Glasgow, where he worked with Ernie Colvin. He completed his doctoral studies under the direction of Larry Overman at the University of California, Irvine, before undertaking a postdoctoral position with David Evans at Harvard University. He began his independent career at UC Berkeley in 1998, moved to Caltech in 2000 as the Earle C. Anthony Chair of Organic Chemistry, and joined Princeton University in 2006, just down the road. He served as department chair from 2010 to 2015. Sir David shares the 2021 Nobel Prize in Chemistry with Benjamin List, quote, for the development of asymmetric organocatalysis. He was knighted by Queen Elizabeth II in July 2022. His research interests encompass a wide range of organic chemistry, including the development of new areas in organocatalysis and photoredox catalysis. Tonight's lecture will discuss the advent and development of asymmetric organocatalysis in the MacMillan Laboratory, exploring concepts of chemical reactivity, catalysis, and the asymmetry of organic molecules, as well as the impact of organocatalysis on modern synthetic chemistry and its real-world applications. Sir David is also kind enough to share a discussion tonight of the life-changing experience of becoming a Nobel Prize winner and how this experience shapes one's perspective of science and society. So now it is my great honor to present our 2025 Ullyot Public Affairs Lecturer, Sir David MacMillan.
Thank you. Okay, well, to begin with, thank you, David, for that very kind introduction. Also, thank you for calling me Sir David. No one ever calls me Sir David. And please, I always tell people, please, you don't have to feel like calling me Sir David. In fact, the only person I insist call me Sir David is my older brother, Ian. With that being said, I'm going to give a talk tonight. It's not really going to be a particularly technical talk. The way I'm going to do this is I'm going to break it into 3 parts. And it's basically just the 3 questions that people have asked me since I won the Nobel Prize. That's really all the lecture is going to be, these 3 questions. So the questions are, where are you from? Because you speak funny. The second thing will be, what did you do to win the Nobel Prize? And then the third thing will be, what's it like to win the Nobel Prize? So that's what I'm going to talk about. Those are going to be the 3 parts of the talk. And it'll take about 40, 45 minutes, somewhere in that ballpark. Okay, so first one, where am I from? Okay, so I'm from Scotland, and this is a map of where Scotland is, and I apologize if this is insulting to you, if you already know where Scotland is. But I'll tell you, the vast majority of Americans have no idea where Scotland is. But there's a really easy way, I tell people, there's a really good mnemonic to remember where Scotland is. Scotland is always on top of England. It's always all right. Always. Very simple mnemonic. All right. Okay, so I'm from Scotland, and you can't really see, it's kind of faded out. But the map of Scotland is here. And this would be Glasgow, and this would be Edinburgh. And I actually grew up in a place called Bellshill, which is a small town outside of Glasgow, and it's a steelworking town. My father was a steelworker, my mom was a maid, and that's where I grew up. This is a photograph to show where we grew up, and this is a council house where we grew up in. A council house is, when you can't afford your own house, the council let you rent a house from them. And this is a photograph, you can tell it's very much from the 70s, based upon the wallpaper and the curtains and the hairstyles. So you can see that that's the 1970s. And I always tell people we didn't have much money, but we were the wealthiest people in the world, because in Scotland, humor is such a big deal. And laughing every day, especially at yourself, is such a big deal. And I would argue that we were a really wealthy family and had an incredibly happy childhood growing up with all these people. Okay, so when I was younger, though, my brother Ian decided to do something really remarkable. So what did he decide to do? He decided he wanted to go to university. Now, I know that doesn't sound completely remarkable, but at that time where we lived, he was the first person in our school who ever wanted to go to university. He was the first person in our town who ever went to university. And this was very controversial. My mom and dad were just really convinced he was lazy and trying to avoid going to the steelworks, which was undoubtedly true. But he was determined, and off he went. And he eventually got a degree in physics. And a week after he got his degree in physics, he got a job. And the job paid more money than what my father made after 30 years of being in the steelworks. And it was right at that moment that my mom and dad came to see me and said, "You're going to university." So the biggest decision of my career, educationally, was not made by me. It was made by my mom and dad through my brother Ian. So that's what I did. I went off to university, and the formula was to do physics, because that's what my brother did. But as it turns out, I was terrible at physics, and I really didn't like it. And I almost left university. But fortunately, along the way, I found chemistry, and in particular, I found organic chemistry. I really loved organic chemistry. And I quickly changed my major, started doing that, worked on that, and then after 4 years, I graduated with this group. This is an amazing group. This is around about 1989. And at this stage, I decided I wanted to do a PhD. Now, one of the things I always tell younger people when I'm giving, especially this talk, a phrase I always use is, education is your passport to the world. And I truly believe that. And at this moment, I decided, previously I hadn't even thought of going to university. Then because of my brother, I went to university. And now I decided I wanted to do a PhD, and I decided I wanted to come to the USA. I wanted to come to USA because I love American sports, I love American television, I love Starsky and Hutch, I love Cheers, you know. And if there's any younger people who don't know what that is, just ask your parents. But I really, really loved America. So I decided I wanted to do a PhD. The problem was, how do you get to do a PhD in America? So what I did was I saved up and I bought these things here. These are airmail envelopes. And for those of you who are not old enough, this is before there was anything like email. And you had to use these type of things. And I had to basically get a part-time job to save up to buy airmail envelopes so I could write to people in America. And I sent off these letters, and it went in sets of 5. I did 5, 10, then 15, 16, 17, 18, writing to lots of people, and got absolutely 0 replies from all these different people. But the 19th letter received a reply, and it was from this gentleman. His name is Hal Moore. He was a chemist, and he was the dean and a founding member of the University of California, Irvine faculty. And he was a brilliant guy, and he sent me back a really nice letter. And the really nice letter basically said, "You're an idiot. No, seriously." And he said, you can't get a PhD in America by writing letters to people. It doesn't work that way. He said, he sent me a general catalog for Irvine, and he sent me an application form. And I filled it out, and I sent it off, and I was accepted. And off I went to California. Now, I always remember this, moving to California. This was 1990. And I grew up just outside of Glasgow. And the weather, we're just talking about being rainy and cold, that's pretty typical summer weather in Glasgow, right? That's really Glasgow weather. And I left Glasgow on a Tuesday morning and landed in California, Los Angeles on a Tuesday night. And it was just an enormous sort of culture shock. I remember I had to go out and get an apartment, and I went to this apartment complex, and I always remember this lady saying to me, you know, at this apartment complex, we have 4 tennis courts, we have 6 swimming pools, and we have 8 jacuzzis. And I looked her right in the eye and I said, "What is a jacuzzi?" and she said, "A jacuzzi is a big hole in the ground, they put hot water in it, come on a Friday night with some beer, you'll have a great time." And it turns out she was right. So this was me, and I had a fantastic time. And to this day, my wife, who's sitting in the front row, will tell you, I will not stay at a hotel unless it has a jacuzzi. It's a very, very important thing. All right, so that was then. All right, I'm going to jump ahead in the story and go to 2021. And 2021 is when I found out that I'd won the Nobel Prize along with Benjamin List for a thing called organocatalysis. So we're going to jump into a little bit of the science now. Okay, so organocatalysis. The second question that people ask me all the time, what on earth does this word mean? What does organocatalysis actually mean? Now, I know a lot of you are chemists, but some might not be. So I'm going to walk you through, first of all, what is catalysis? So catalysis, the easy way I like to explain catalysis is if you look around this room right now, absolutely everything you can see with your eye is made by a chemical reaction, absolutely every single thing. This is a photograph of my office in Princeton. It's a little bit messy, but if you look at absolutely everything in this picture, everything is made by a chemical reaction. So if I focus in on just one thing, so I'll focus in on this one. This is my coffee cup right here. If you look at this chemical reaction, that's the chemical reaction that makes caffeine, which is the stimulant that we find in coffee. Now, chemical reactions require energy. They're typically not spontaneous. And the way that we show this is this energy diagram. Now, that sounds technical. Don't worry, it's not going to get very technical. But this is the energy diagram for these 2 molecules becoming caffeine. And when I explain this, for example, to high school students, the way I explain it is, imagine that every single day when you were walking home, you had to walk over a really large hill every single day just to get home. That would require a lot of energy. And that would get frustrating and annoying after a while. But imagine you could build a tunnel that went through that hill. That would make it so much easier to get home every single day. And that's exactly what catalysis is. It allows existing chemical reactions to become easier and faster. And more importantly, if you take anything away from this talk tonight, it allows chemical reactions that were previously impossible to become possible. That's the biggest deal, I think, about catalysis. Okay, now, people often ask me, well, does catalysis really impact my life? And it impacts everyone's life in so many different ways. I'll just show you one example. This is the global population of the world for the last 2,000 years. And you can see it's basically flatline up to about the beginning of the 20th century. Then there's an inflection point where it jumps all the way up to 8 billion people, where we are now. As it turns out, we could not have 8 billion people on Earth right now if it wasn't for one catalytic reaction, the conversion of nitrogen into ammonia. So why do we need this catalytic reaction to have 8 billion people on Earth? Well, it's really simple. We need ammonia to grow crops. We wouldn't have enough food for 8 billion people without this one catalytic reaction. One of my favorite all-time statistics is if you think about your body right now, and you think about all the DNA and all the protein that's in your body, and think about all those nitrogen atoms that are in your body, 50% of those come from a factory in Germany. If that doesn't freak you out, nothing will. I mean, that is a phenomenal statistic. Also, it's a chemical reaction or catalytic reaction that uses up 1%, it's actually almost 2% now of the world's energy supply on a daily basis, which is, again, really incredible. Other statistics, 90% of industrial scale chemical reactions with catalysis, 35% of the world's global GDP is based on catalysis. And if we think about trying to overcome climate change, that number has to go up. It can't go down. Okay, catalysis, that was catalysis. So second part, what does organo mean? Okay, so to explain organo, I'm going to take you back to 1996. What were the branches of catalysis, or what were the areas of catalysis in 1996? And there was really two of them. The first one is biocatalysis, which is using the enzymes of life, which is, there's thousands and hundreds of thousands of catalytic reactions happening in our bodies right now. But for the external world, the number one type of catalysis that the world uses externally to our bodies is metal catalysis, completely human-driven. So why 1996? Well, 1996 is when I finished my PhD, and I decided I wanted to go to Harvard to work for this gentleman. His name was Dave Evans, one of the greatest organic chemists who ever lived. And he was someone who worked on metal catalysis. So I wanted to join Dave's team because I wanted to learn about using different metals to do different types of catalysis. And I learned an enormous amount from Dave Evans, and I learned an enormous amount from his team. I was incredibly lucky to be part of that team. But along the way, you realize that if you're going to do metal catalysis, every single day you're going to use this thing. So what is this thing? This contraption, you probably recognize it, is a glove box named after these huge gloves here. And the reason why you would use this contraption is basically because the inside environment is different from our outside environment. The inside environment is inert, and many metals have to be stored in there because they're not robust enough to live in our outside environment. But as a result of this, I would spend about 8 hours a day in a glove box while I was at Harvard. And after 2 years of this, I started to sort of question this and started to think, why are we spending so much time in a glove box every single day? Now, if you're not a chemist, this is what I would argue is a typical metal catalyst. And even if you're not a chemist, you can sort of look at that and you can sort of see you can divide it almost into two parts. There's a left-hand side and there's the right-hand side. If you look at the right-hand side, this is the metal center. This is some metals, not all metals, but some metals can be expensive, they can be toxic, they can be non-sustainable. I'll give you one example is palladium. Think about palladium. Palladium is in your iPhone, palladium's in many of your cars. We only actually have enough palladium left on Earth to last 90 years, and then we won't be able to get any of it back, which is an incredible statistic if you think about it. Now, on the left-hand side, the thing that holds the metal in place while it does the chemistry, that's the organic molecule. And organic molecules, which come from life, as you would expect, because they're so abundant all over the world, they're inexpensive, they're safe, and they're sustainable. And if you think about this, life moves on, it goes right back into the life cycle. So every single thing about organic molecules are recyclable. They're completely sustainable. They constantly recycle through the world. So the question for me was, well, what if we use only the organic part as the catalyst, given it's so abundant, it's so recyclable? And ultimately, this became known as organocatalysis, organic and catalysis together. Okay, so in 1998, I landed a job as an assistant professor, and I landed a job at UC Berkeley. And I love this photograph because this is my very first group in our very first year. And I love it because it's 10 past 10 on a Friday night. And you've got this young group who are in there working really hard, trying to have an impact, trying to make a difference. So what were we going to work on? Well, I decided, we wanted to do this thing called organocatalysis. Now, it wasn't called that then, but the reason why I was interested is, first of all of these molecules that you could potentially use are widely available from nature's building blocks. They're not sensitive to air and water, much like you and I are not sensitive to air and water. They're so abundant, they're typically very inexpensive. You don't need to use these glove boxes. They're really easy to handle. And they're non-toxic, they're recyclable, they're completely sustainable. So all of that sounds wonderful. What was the catch? The catch was, even though I wanted to do this, I had absolutely no idea how to do it. I knew I would like to do something in this world, but I didn't know what that actually looked like. I had no way to approach it. However, one day I was in lab, and one of my very first students, his name was Tristan Lambert. He is now a very accomplished chemist. He is now the chair of the Cornell chemistry department, so you can tell this was quite a while ago. And in his first year, he came up to me and he asked me the question. Now he said, what is the mechanism of reductive amination? Now, that's a really simple mechanism to explain. And so as a young professor, I ran to the board and started enthusiastically drawing up this mechanism. I said, this molecule and that molecule join, and it's only when they have this configuration electronically can they do the subsequent chemistry. And it was right there, right then, I had the quintessential eureka moment. Because I thought, wait a minute, because if you take that molecule and reversibly forms this one, this looks a lot like a whole field of metal catalysis that had been used to catalyze hundreds of different chemical reactions. So if I actually just draw that in a slightly different way, the way chemists would conventionally write this, on this top line is an equation. It's a type of catalysis called lumolorine catalysis that's been used for literally hundreds of different types of chemical reactions. The one on the bottom line, though we've replaced the metal with an organic molecule, there's basically no examples of doing this. But if these are really simultaneous equations, that means that organic molecules should be able to catalyze literally hundreds of chemical reactions. So, okay, that sounds good, let's go try it. So literally that day, I convinced a first-year graduate student, her name was Kateria Rent. This is her notebook page from that very first attempt, where we took these two molecules. This is what's called a Diels-Alder reaction. We're going to take these two molecules and hope they combine to form that molecule. Here's the chemical arrow, but you can see above the arrow there's no metal catalyst. What there is an organic molecule. So we performed the reaction, go all the way to the bottom of the page, and down here it shows it worked. It worked, and this was so incredible. So I always remember Kateria came, I was in the lab, she told me the result, I thanked her, I left the lab, I walked into my office, I closed the door, I locked the door, I closed the blinds, and then I jumped up and down for 10 minutes. I remember calling my wife at the time and saying, I think we're going to get tenure. And now, the academics will enjoy that joke, that story, because it was true. Number one, it was true. But it's also, when you're a young assistant professor, there's not really much else you're thinking about than tenure. Tenure is literally everything. And that's what was sort of consumed by that. Okay, so at this moment, you have to sort of publish your first paper on this. And so one of the first things we did is I came up with this name organocatalysis. Now, you might ask yourself, naming things. What's in a name? Is naming things important? And I would argue that naming things is really important, and it's not a modern thing. So, for example, and I know there's a lot of science historians here, Jean-Jacob Berzelius, very famous Swedish scientist, he came up with lots of vocabulary that we now use in modern science, things such as catalysis itself, or protein, or polymer, isomer, organic, inorganic. He came up with all of those words. And the importance of vocabulary as it moves into the modern era is absolutely critical. You can't think about the framework or how you even think about fields without thinking about the names that go with them. I'll give you an example, directed evolution, AI, machine learning, nanotechnology, organocatalysis. These are just words that help you build a framework to let the whole community talk about it and understand what it is you're talking about. So that was one thing, but I would say more importantly was we introduced the concept of a generic activation mode. which sounds a very fancy scientific term, but it's actually a very simple meaning. All I was saying here is this idea shouldn't work for just this one chemical reaction. It should be usable for hundreds of other chemical reactions along the way. That was the idea behind it. There was only one problem. The one problem is we'd actually only performed one reaction at that time, this one shown here. And I'm telling the world this is going to work for hundreds of reactions. So we went off to test this, and it went bang, bang, and stopped. It stopped after 3 chemical reactions. So at this moment, I start having a panic attack because I've told the world this is going to work for everything, and it's only working for 3 chemical reactions. I wasn't quite sure what we were going to do. But very fortunately, I had 2 really amazing young graduate students, Joel Austin and Chris Bortz, who came along, and they literally said the following. They said, if you look at this catalyst, and if you remove this 1 carbon here, and you take the top one and you make it into 4 carbons, we predict this will now work for hundreds of different reactions. Now, that's a really, really bold thing to state, and it's very hard sometimes to explain to a non-chemist how bold a statement that is. So the analogy I use, I immediately go back to sports metaphors, because I'm a huge soccer football fan. And this is Zlatan Ibrahimovic. He's a very, very internationally known football player from Sweden. And he was known for doing really bold things. He did really sort of bold maneuvers. So I'll just show you one of them. This is a goalie scores, and you'll see this. That's an overhead kick from 40 yards away. That's an incredible goal, right? That's an incredibly cool. Now, it turns out I actually showed this video as part of my Nobel lecture, which goes out across the world and is seen by literally an amazing number of people. And the next day, there was a lot of newspapers in London got really upset about this. And they said, MacMillan is Scottish, and the only reason they showed this video is because the goal was scored against England. And I actually was kind of like, I thought that was a little bit unfair, but let's watch it one more time. All right, look at that, how good is that? That's an amazing, amazing goal. Fantastic goal. All right, so here's the question. Can we have this bold outcome by changing this catalyst? So we went from this catalyst, which is only 3 reactions, we now change that top carbon to 4 carbons, and now it takes off like gangbusters. Other people start to join the field, Jorgensen, Hayashi, many others, and now as time marches on, we're now hundreds and hundreds and hundreds, if not thousands, of chemical reactions you can use organocatalysis for. So what can you do with it? Well, there's many, many different applications of organocatalysis. I'm only just going to show you 2 of them. First one is for flavors and fragrances, and this is Firmenich, who's a very famous perfume company. And you might say, well, is perfumes a big deal? But if you think about the volume of perfumes that is actually utilized and consumed on a daily basis, it's absolutely enormous. And so Firmenich actually was able to now make Lily of the Valley in 1 chemical step when it used to take them 6 chemical steps by using this. And the energy reduction and the cost savings and the waste reduction, et cetera, and all of this was really, really fantastic. But without question, the number 1 application of organocatalysis has been for making medicines. There's many, many different medicines that are now made using organocatalysis. My favorite example is Talsedupant, which is from Merck. And I'll be honest, the reason I like this is because they used exactly the type of catalysis that we developed on that very first day from that very first notebook page. It was exactly that same approach. And they use it to make this treatment for migraines, which I think impacts like 2 to 3% of people on a worldwide basis. But again, it's now used for so many different types of medicines on a worldwide basis. But there was a third aspect to this which I absolutely did not see coming. And this is something which is now known as democratizing catalysis. And it's basically that organocatalysis is incredibly inexpensive, which means it's very affordable, it's very accessible to the whole world. And I don't mean just accessible for teaching, I mean it's accessible for actual research. So when people often say to me, what is going to be the next big thing for organocatalysis? I always say, I actually don't know. But it's not going to be based upon who has the most money or who has the most resources. It's going to be based upon who has the best idea. And to me, I think that's something that's super cool and very much fits in a lot with my own sort of values. All right, so what does the future hold for organocatalysis? And again, I don't know, but one of the things that I do know is as we think about a scientific community, We have to, in fact, really think about this ever-expanding global population and the energy we're consuming, et cetera. And we have to invent new types of catalysis that's not only going to deal with things like climate change, but it's also going to deal with sustainability and the fact that we're not just going to chew through all of the Earth's resources in a non-returnable way. So that does include organocatalysis, biocatalysis, but things like photocatalysis, electrocatalysis, but we actually have to start inventing a lot more of those. And the time to do it is actually now. It's really important that we actually do that. Okay, so that's all the science that I'm going to talk about. In the last 15 minutes or so, if I have 15 minutes, I'm going to just tell you about what it's like to win the Nobel Prize. That's the third part of the talk. And the question everyone always sort of says to you is, oh, how did you find out? How did you find out that you won the Nobel Prize? So the story goes like this. It's October 6, 2021, and it turns out I'm lying in bed. It's about 5 o'clock in the morning. And I'm lying in bed sleeping, and all of a sudden I feel it in my ribs. I feel this elbow hitting me in the ribs, and it turns out it's my wife, Jean. And she keeps going, your phone keeps buzzing, your phone keeps buzzing. Now, it turns out she doesn't have a Scottish accent, so she didn't say it quite like that, but she did say, you know, your phone's buzzing, can you deal with your phone? And I was like, I'm not getting up, I'm tired. So I didn't get up, so she gets up, walks around the bed, picks up my phone, and moves it to the window ledge so it would stop annoying her. But as she's coming back, she says, it looks like someone from Sweden's trying to reach you, and it looks like Ben List, the other winner's trying to reach you. So I'm like, what? So I get out of bed, and I pick up, and you probably can't read this, but this is the text on the left-hand side, and it says something from Göran Hansson, Royal Swedish Academy of Sciences, but the only thing I notice, it says Dr. MacMillan. And I'm like, who the hell is Dr. MacMillan? All right. So I'm like, this is clearly fake. All right. So then the second part of it is that Ben contacts me, and I actually called him, and he says, we did it. And I said, what did we do? And he goes, we won the Nobel Prize. And I'm like, I don't think so. And then basically I convinced them over the next 10 minutes that this was clearly a prank that was getting played. Because at Princeton, they'd have this big end of the year sort of big party where they just make fun of the faculty for an hour. And they do all these great practical jokes. And I'm like, I'm one step ahead of them. I can see that this is... Anyway, so I bet him $1,000 it's a prank. And Ben is very nice and actually says, that's really nice. We can use the $1,000 to go out for dinner together. And I respond, no, going back to sleep, cheers. And I literally went back to sleep, as my wife will tell you. So I went back to sleep for about 40 minutes. Then I woke up about 40 minutes later, and I thought, well, today is the day the Chemistry Nobel Prize comes out. I wonder who won it. So I go downstairs to the kitchen, and I have a laptop on our kitchen counter, and I open up the laptop at the kitchen counter, and I go to the New York Times website. So I open up the New York, and this is what I see at the New York Times website. So this is what I see, and I look at this, and I thought, well, that kind of looks like Ben List, but who the hell is that? And I sort of noticed my name underneath this. And people often say to me, what was it like the moment you realized you won the Nobel Prize? And I went, well, on one level, I was very much elated, but I was also somewhat offended by, like, this is, what is going on? All right, so that kicked off just an incredible day. I have to say, it was one of the best days of my life. And this is my group. It's 10 past 10 on a Wednesday morning. You can't buy alcohol in Princeton till at least noon. But my group has rustled up a huge amount of alcohol already, even before I actually got there. And then the other thing you have to do is you have to do all of these interviews, and you're a chemist. You're not media trained or anything. And suddenly you're doing all of these interviews with like the New York Times and the Wall Street Journal. And so I ended up doing an interview with the BBC in the morning, BBC Scotland, and it went really well. And so they called me back and said, the BBC Britain from London wants to do an interview at 2 p.m. Can you do that? I was like, sure. So I went on that, did that, and that went really, really good. So I'm feeling pretty good at this point. And then they called me back and said, we would like to put you on at 6 p.m. to do the BBC World News Live. And I'm like, what is that? And they're like, well, it's the World News. It's live to the whole world. And I'm like, okay. So I'm like, I'll do it. And you should go online and listen to it. It's still online. It's a complete train wreck. It's really terrible. So it starts off with the journalist or the news anchor sort of says to me, Professor MacMillan, so you're the person who invented molecules. And I'm thinking, oh man, I'm like, And then I had to try and explain molecules to him, and it just didn't really go anywhere. Anyway, if you're ever bored, go listen to that interview. All right. So this is, in 2021, we had this ceremony, and it was in Washington, D.C. because of COVID. And it wasn't yet in Sweden, I'll come back to that, but they had one in Washington, D.C. And this was absolutely incredible. And this is a photograph I actually have on my office desk. And I love these photographs. This is my family came over from Scotland. That's my family in America. And I love this photograph on the left for so many different reasons, but I'll try and explain it to you. So the first thing you'll notice is that I'm actually wearing a kilt. And if you don't know what a kilt is basically the Scottish national costume. It's what men wear. It's like a tartan skirt. And it turns out I'd never worn a kilt before, but I thought, I'm Scottish, I've got to get a kilt, right? Now, I couldn't find anywhere that would make a kilt around where I live. So what I did was I went to a tailor and got measurements taken, and they sent it back to Scotland, and they sort of did a hurry-up courier thing, made it, and then sent it back, and it shows up the day before the ceremony. So I put my kilt on the day of the ceremony, and it's super, super tight. It's really, really tight. It's so tight, my wife described it as a pencil kilt. All right, so I'm wearing this thing. So they call out my name, and I have to go get the medal. So I sort of shuffle up, and I get the medal, and I turn to the world press and sort of do that, and then I shuffle back to the thing, and I'm like, this is not good. And so that night, we went to this fancy gala, and you can see here, and there was dancing. There was all this great, and I couldn't do any dancing because my kilt was too tight. So I was kind of like frustrated. Anyway, so we go back to the hotel after all of this, and we go to the hotel bar, and some of our friends are there. And there's a woman, and I'm explaining to them how I'm annoyed and frustrated about how they messed up my kilt. And there's a woman there, her name's one of my friends called Christina Crammell, and she looks down at my kilt, and she goes, what is that? I was like, what's what? She goes, what's that thread that's sticking out? And I looked down, and it turns out it was a thread they had put in the kilt to hold it in place for shipping while it was being sent across. And she leans down, and she pulls out the thread, and the kilt goes, vroom, like that. So the reason why I love this photograph is because what should be my highest moment of intellectual achievement, and all I see is the world's biggest idiot, right? It really is. All right, now the other part of that I really love about the Nobel part when it all happened was the Nobel people contacted us right afterwards and said, all right, you've won the Nobel Prize. Can you send us photographs of you as a baby? And I sort of said, why? Why do you want photographs of me as a baby? They said, we want it for our website. And I was like, that still doesn't answer the question, but okay. So I went back, and myself and my wife, we went all around our house trying to find photographs of me as a baby, and I didn't have any. So I contacted my sister, who was still back in Scotland, and she went through all of her photographs. She found these 3 photographs, sent them over. They're now on the Nobel Prize website. Now, after about a month, I was on the website and I was looking at this, and I realized this is one of the greatest practical jokes that's ever been played. Because if you look at that picture right here, that's not me. That's my sister. And she recently confessed to this, and it was really pretty cool. And she's also very happy about the fact that she actually has 2 photographs on the Nobel Prize website, which is also. But this is the mind of a Scottish person, just to sort of to keep them in. All right, so Nobel Week was 2023 in Stockholm, so we couldn't have the celebration in Stockholm in 2022. So they invited us over in 2023, and it was phenomenal. It was just an amazing event. And that's me, and you get to sort of get all dressed up and dapper and wear your white bow ties, and the whole family. Just an amazing, amazing week. And you get to hang out, and you get to meet with royalty. This was Princess Sophia, and I always felt bad for Princess Sophia, because she had to spend 4 hours talking to a chemist. I mean, you have no idea what that must be like. But she was a lovely, lovely, charming, charming person through the whole thing. This was very cool and very unexpected, and it was a really interesting thing. So one of the things they do that they don't tell you about is they take you into what was Alfred Nobel's office, and it's been kept the way it was since, I think, 1901. And they sit you down, and then they put some books in front of you, and I'm like, what are these books? And it's all the books of all the Nobel laureates through the ages who've all signed the book. And so you start paging through all these books, and it's like Einstein's there, Marie Curie's there, all the Curies are there. And then you're paging through, and then you get to this one page that has your name on it. and you have to sign it, and it's one of the most surreal moments of my entire life. But what was absolutely phenomenal about it was I was there with my wife, Jean, and to be able to sort of share that moment with her was just so incredibly special. So I always include this photograph in any talks I ever give about this because it was such a cool moment. All right, now, one thing that happens to you when you win the Nobel is you do get to meet lots of interesting people along the way, and these are just some of the people that you met. As mentioned earlier, I found out that I had been knighted by Queen Elizabeth II, and this is my family all over Buckingham Palace. That's my sister, the aforementioned sister right here. The Scottish people should not be allowed in Buckingham Palace, but anyway, so there she is right there. And the Queen had passed away by the time I actually went over to do the ceremony. But what happened was Prince William was there to do it, and he did. You'll see the kilt is now working perfectly. But he did the whole thing with a sword. And then the thing that happens afterwards is you have a chat with him for about 10 minutes, which is really, really cool. And so he starts talking to me, but it became pretty clear pretty quickly that whoever had prepped him really badly. Because he says to me, Professor MacMillan, I heard you're the man who's getting all the plastics out the ocean, which is not what we do at all. And so but I was very nervous, so I said, yes, we are. And in the back of my head, I'm thinking, why am I lying, you Prince William? Anyway, but it was an amazing event, and my family were all there. My daughters, and Danielle was one of them, was sitting in the second row, told me afterwards that in person, he's very tall, and he said he's incredibly good looking. And so the Buckingham Palace press corps sent us a photograph afterwards, and I love this photograph. I hope you can sort of see it. It's of my younger daughter, who's just basically met Prince William. I don't know if you can see her eyes, but she just absolutely loved it. Now, there's a quick follow-up to this story. Recently, we were in London, and I had to give a talk, and I gave this talk, basically. And when I sat down, and they already had my slides at the back of the hall, when I sat down, and it said HRH is on the seat beside me, and I said, who is HRH? And they're like, oh, Princess Anne is coming to your talk. And I was like, she's going to come to the chemistry talk? And she said, yes. So she came and she sat through all of my talk. And she was absolutely fantastic, and we had an absolutely brilliant time. But at some moment, and I was telling all these stories, and she's laughing away, but at some moment I realized I had to tell the Prince William story about how they prepped him badly. So I tell this whole story, and everybody's laughing, and I look over at Princess Anne, and she's got her head in her hands, and she's sort of shaking her head. And I'm sitting there thinking, on stage, I'm thinking, I just threw Prince William under the bus with Princess Anne. That's terrible. Anyway, it was a very surreal moment. All right, I'm almost done. All right, now I showed you this goal earlier. This very. Now, I'll be honest with you. When I did put the video in my Nobel lecture, I knew I was kind of doing this a little bit as a bit of fun towards England because half my friends are English, and it was just a bit of fun. It was a bit of banter, and I thought no one would ever care that I did this, right? I thought no one would even think anything of it, except this whole business about everything that happened to the newspapers. But the thing is that the day after, the Times of London, probably the most substantial newspaper in the whole of the United Kingdom, wrote this whole article about this video. And you can probably read this part up here, but the thing which is, the thing which is, I think, even better, you probably can't see it, but this is the byline I love so much. It says, a Scottish professor mocked the England football team while accepting his Nobel Prize for Chemistry by revealing a spectacular goal against them helped inspire his scientific breakthrough. Oh, that's just fantastic. All right. Yeah, all right. So other people you get to meet along the way, and I'm almost done, I promise you I'm almost done. Other people you get to meet along the way after winning the Nobel. So obviously, I think most of you probably know who Star Trek is and William Shatner. And I got a call from William Shatner's assistant who said, would I like to be interviewed by William Shatner for a show? And I said, sure. And so I went on and did the show with him, and it was fun. We chatted for about 45 minutes. And then there was a good half an hour after we stopped recording. We were just sort of shooting the breeze and having a good time. And then afterwards, his assistant contacted me and said, Bill really enjoyed talking with you. Do you mind if he ever has questions, he can sort of call you up and ask you questions? I was like, sure, that's fine. And one of the things you realize when you win the Nobel Prize, people suddenly believe that you're Wikipedia, right? They think that you can answer almost anything. So my favorite example with this was William Shatner. I was on vacation, and he called me up, and he said, David, what is a photon? What is a photon? And I'm like, this is amazing. Captain Kirk wants to know what a photon is. And anyway, so I kept up this really nice relationship with this, and that was all great. And then I was contacted recently by the BBC, and the BBC now want myself and William Shatner to do a podcast together, where he'll ask me scientific questions, and I will attempt to answer them. And I think he's actually going to do a better job than I will, have been able to answer half of these. But anyway, stay tuned. That I think maybe this was me. I was out in Los Angeles recently, chatting with them about doing this podcast. So people often ask me, "Do you still get nervous before you give talks?" And I used to get nervous all the time. I'm still a little bit nervous, but probably the most nervous I've ever been is after you win Nobel prizes. People ask you to give graduation speeches, which I hadn't really done before. And that's fine, but sometimes you're never quite ready for the enormity of them. This one was at NC State. It was actually last year. And it was actually 28,000 people where you have to stand up and give a 20-minute speech. And I'll tell you, your adrenaline really kicks in when there's 28,000 people. And I remember just sitting at the back, and this was the panoramic view I took of all these people sitting there. And it was an incredibly fun thing to do. I have to say, it was one of the best things I ever got to do. Now, I'll finish off by saying this one last thing. I would argue that, COVID was very difficult for a lot of different reasons, but one of the things that COVID did do was it introduced us to Zoom. For good or for bad, it introduced us to Zoom. From my perspective, it's been fantastic because now one of the things that happens is you get contacted by high school kids all over the world who want to chat with you, or teachers want you to talk to their class, and you can do it. You can do it over Zoom. It's really easy. But one of the ones which had the biggest impact on me this was a couple of years ago now, and the Ukrainian ambassador to the US contacted me and said, would I give a Zoom lecture to all these high school kids in Ukraine who'd been displaced due to the war? And I said, sure, but I had tremendous trepidation about doing this because I really was sitting there thinking, I do not know how I can identify with what these people are going through. I just can't even begin to imagine how this is going to be. And I remember going on and I talked to them, and they were lovely, and they said to me, if the sirens go off, we'll have to leave the Zoom call because we have to get in air raid shelters. And I'm like, what on earth is going on? This is crazy. So I gave them a lecture, and one of the things that just blew me away was just the level of excitement that they had to talk about chemistry and to talk about science. And if you're ever having a sort of bad day and you sort of want to make yourself feel better, for me, I just think about these kids and think of what they're going through and think that they're so jazzed about chemistry. And they just want to be more involved with it. It's just an amazing, amazing thing. Actually, it really is phenomenal. All right, now, a last thing I'll point out is after we won the Nobel Prize, I found out that you win about $500,000. So we won $500,000. And I decided it didn't feel right to keep the money. It doesn't feel that appropriate. You win the Nobel Prize. Why do you need money? So we decided that we'd create this charitable fund, which is basically a fund that allows or is for underprivileged school kids in Scotland to get the chance to go to college or go to university. I was actually on the BBC talking about it, and it took off, it went viral and went all over the world. And as a result, lots of people from all over the world started to donate to it. And a very well-known wealth fund actually came in and said they would manage it for us. And now they've managed it, and it's become a pretty large fund, which has been fantastic. It's named after my mom and dad, who passed away many years ago. But the key thing here is it really does had a major impact. Now, last year we sponsored 90 different kids in Scotland. So that's been really just an amazing thing to actually be part of. I finish every lecture by thanking my family. This is us. This is our three daughters. Danielle is in the front. This is us on the Harbour Bridge in Sydney. And I like to point out, education is your passport to going to see the world. And this is my wife, Jean, who's also a chemist, and she's down the front row. And I always finish by telling the following story. She's actually an amazing medicinal chemist, and she actually has 2 drugs on the market, which is pretty incredible for that. And I was actually down in Brazil, and I was on a television interview, and they said, Professor MacMillan, are you one of the best chemists in the world? I said, I'm not even the best chemist in my own house. I mean, anyway. So it turns out she's an amazing chemist, but she's also an amazing mother. She's my best friend, and we have a brilliant time traveling the world together, and I always like to thank her at the end of every talk. And then lastly, thank you all for your attention. Thanks a lot. Oh.
That was great. Stay right here. David, Sir David, that was superb. I'll only say that the next time you come back, we want to see the kilt. This is all great, but let's have the kilt next time. Doubtless, you have questions, and we have a few minutes for questions, so my colleagues will come find you with the microphones, and sir, I invite you to take the audience's questions.
Thank you, Sir David. Sorry, I couldn't resist. So I'm not a chemist, but I found it absolutely comprehensible, entertaining, and riveting. And so my question is, at a time when science is under attack from everywhere, at least in this country, how do we get more people to communicate science like you just did?
Yeah, it's a great question. I think it comes down to access, and it comes down to advocacy, which sounds very boring, but I was in a meeting in Germany, and they had all these high school kids from all over the world there, and someone who was a high-up person at Bayer said, we want you to do an exercise, how do we get the world to care more about science, and write your answer down on a yellow sticky. And I'm thinking, it's going to take more than a yellow sticky to solve this problem. But this young high school student put up this thing, and I thought it was, maybe you would disagree with this, I thought it was profoundly clever, where she said, why don't we get people that we care about, like Taylor Swift or whoever, to just say that science is awesome? And that was it. And I was like, that's genius. I mean, it really is genius. And you start to realize it's about, scientists talking to scientists is easy. We all believe in it, but it's how do you sort of connect? And well, I think we have to go through people who do connect with just an enormous audience and get them to advocate and say, science is kind of important. It's kind of really incredibly important. If you care about climate, you care about the climate change, you care about your future, science is kind of going to be the way forward here, right? And if we did a little bit more of that. So I'm a big advocate for, we have to get out and do our thing. But I think what we really have to do is to connect with people who are communicating extraordinarily well, especially with a younger generation. I think that's the only path forward to actually do that. But I do think your question is incredibly on the money. It's an incredibly important question.
So this is all well and good and very exciting, but how was that game last night?
What a game. So when so I don't know if nobody probably, you know this, but so Scotland last night qualified for the World Cup. To put this in context, they qualified for the World Cup for basically the first time in 30 years. 30 years, 28 years, but 30 years the first time they qualified. They qualified with scoring a goal which happened 3 minutes into injury time at the end of the game. You can't understand the level of pandemonium that's going on in Scotland right now. It's unbelievable. I've spent the whole day, when I should have been getting ready for this talk, I've spent the whole day watching videos of people in pubs going crazy, just watching that goal going in. I mean, it's just unbelievable. There's a very, very famous football coach called Sir Alex Ferguson. He was the coach of Manchester United and we've become reasonably good friends. We were over in Old Trafford recently. I went to a game with him. We've been texting back and forward all day about Scott. He's the greatest football manager in the history of the game, and he's excited as every 8-year-old child in the world about Scotland going to the World Cup. So as much as I'm excited about Catalysis tonight, I'm way more excited about Scotland. Thank you for that question. Yeah.
Suggestion first, coming back to the first question, maybe you should partner with or collaborate with, is it Lin-Manuel Miranda that did Hamilton?
Yeah.
And do a Broadway musical
No, it's
that
exactly
makes
right.
chemistry
No.
cool.
No, that's a
That would
brilliant
be cool.
idea. Why
'cause
not?
That's kind of how I learned history. But I am a chemist by training. I have two questions. I'm a polymer chemist. I'm just interested in a little bit of chemistry of the big bulky trimethyl group that you put on, like
Why did that work?
Why did that work is my first question. And then the second question, because I'm a chemist turned business person, did you patent that, and
I'll answer the second question first. We didn't patent it, and we tend not to patent. We haven't patented any chemical reactions that come from my lab. I'm a big fan of, you're basically you're getting paid NIH dollars, by NIH to do things for the world, and it's taxpayers' funds, and you should put it all back out there for the world, right? And so, and that's not to suggest I'm not interested in commercial. Now I'm about to ruin it by telling you. I'm not against commercial ventures. I've certainly been involved with sort of biotech companies and things like that, where the only pathway forward would not be in academia, because it would be so applied and it would not be good use of a graduate student's time to work on the things that you were going to be doing. But I do think it's really, really important that the fundamentals in chemical reactions, chemical reactivity has to get out there for everyone. And I think the organocatalysis part, we were just in India for 2 weeks, and organocatalysis is massive in India. And it's massive because it's cheap, and it's affordable, and there's nothing better than that, I think. In terms of the methyl thing, now we're going to get really technical. So what it is on nitrogen, there's a lone pair. And the lone pair, the first step it has to do is react with this carbonyl. And because it's got those two methyls, one of those two methyls was blocking it. So they said, well, why don't we get rid of one of the methyls? But the problem is then there's two different what's called amine geometries that will go back and forward. So they had to control it. So they said, well, if I make it into a big T-butyl, it's going to push it this way, but give almost complete umbrella coverage of one face and leave the other face open. Now, at the time, I thought there's no way on earth this is going to work. But being a reasonably, which I've learned to do in academia, is you never tell a graduate student or any student that that's not going to work. You just sort of say, yeah, you should definitely try it, thinking it's not going to work. But then they come back in and they go, it worked. And you're like, I knew it, right? Yeah. So it was a brilliant insight that they had. And it was, just, changed the whole course of the whole thing based upon the insights that they had.
Given that, how would you progress in the scope? We talked about AI every other day, whether or not we're using that robotic synthesis. Could you, I'll call it an older sort of organicer, I don't think in those terms, but clearly in your area of organic catalysis,
Right.
that has to be a meaningful path.
Yeah, so the question is, what does AI do for chemistry? It's the question everyone asks everywhere you go. And it's a tricky question to answer because no matter what you say, if you say anything negative about AI, you're almost certainly going to end up on the wrong side of history, right? Because AI is going to do a lot of things. I will say, though, at the present time, AI is really, really good at optimizing things. So if you've got something that's working a little bit, it's very good at making it work really, really well. The thing, though, it cannot do as of yet is invent a completely new chemical reaction, because it doesn't have the data to do that. Because to invent something completely new, it has to have some kind of pattern recognition on which to base it on. But if that pattern doesn't exist yet, then it's kind of hard for it to do the invention. The thing that it can do, though, is, and I'm a big advocate for this, it could come up with ideas. Like, for example, if it said, what if you could take this molecule and these molecules, which are abundant on Earth, and somehow glue them together? Then you would solve this huge energy problem of making these molecules over here. And I think these conjectures that it can do, it could do that. I think it could be really, really useful. I'll give you one. This is not something AI came up with. This is a goofy idea I came up with, which is, and it was talking to a lot of people in the US Navy about aviation fuel and the amount of energy that goes into aviation fuel. And the fact that we're not going to change aviation fuel easily for a whole bunch of different reasons. We're not going to use batteries for planes because there's a couple of different reasons. One of them is they don't change weight, and then the other one is that basically they're just too dangerous to put in airplanes. Whereas aviation fuel, they can sort of control. So no one's going to change aviation fuel. But the problem is, like, kerosene and those isomers are really hard to get their hands on. But if you could dimerize hexane, or you could dimerize pentane, you could really revolutionize that world overnight. So that's something that my group's working on, is how do you do that? It's a really, really tough problem. But at the same time, just coming up with the question was the hardest part. Because once you know the question, now it's just a matter of keep thinking, trying, come up with things and do it. And eventually someone's going to do it. But I think the question was the harder part of sort of realizing. And I think AI could sit around going, we need C12 and we need C14. We've got tons of C6. Why don't you guys just go dimerize C6? And I think that those will be the type of things, in the short term at least, AI could be really, really useful for. So I don't know if that answers your question, but it gives you a sort of slice of where I think we're at the present time.
I think we have time for one more question. Hand up right here.
What turned you off about physics?
I was not smart enough to do it. It's kind of funny because physics, for me, I always tell people I didn't find organic chemistry found me, because I just started doing organic chemistry and it all just made complete sense at a time when everyone around me is going, this is the most difficult course I've ever taken. And I think organic chemists, it's kind of funny, you talk to other organic chemists, they'll all tell you exactly the same thing. Like, why do people find this hard? We can't quite understand. The other part of physics is, physics I found just so abstract at certain times. You know, I went to see the entanglement talk, part of the Nobel lecture, and at the end of it, the Nobel laureate says, I've just given the Nobel lecture on entanglement, and I don't think I understand it. Which I thought was very, very cool that he said that. But it was just, it's so abstract at times. I'll tell you one third thing, and that is the sort of rivalry between physics and chemistry. So my brother is obviously, my older brother is a physicist, and I'm a chemist. And I won the Nobel Prize, right? And I go up to him and went, hey, I won a Nobel Prize. Not bad, eh? He goes, it's a Nobel Prize in chemistry. It's not a Nobel Prize in physics.
Thank you all for your questions, and David for enlightening us on everything from organic catalysis to soccer. We'll never look at it the same way again. It is our tradition at the Science History Institute to honor our Ullyot lecturers with the presentation of the Philadelphia Liberty Bowl in recognition of their extraordinary accomplishments in service to science and to humanity. It is now my pleasure to invite to the stage Preston Moore, Professor and Chair of the Department of Chemistry and Biochemistry at St. Joseph's University, to present the Liberty Bowl to Sir David. Preston.
Oh, wow.
This is
Thank you. Fantastic.
given to you from us to you to say thank you for a wonderful lecture.
Thank you so much. Thank you.
We'll do a quick photo, maybe when we go over there. Don't worry, it won't break it.
Thank you. Thank you.
Well, so David, we want to thank you again for a wonderful, informative, and highly entertaining program. Thank you. And now I want to thank you again. Thank you for being here, and I wish you all a very good evening. Much appreciated.